we're going to start deriving the idea of higher order derivatives and how we're going to take care of those numerically. So you might recall in the first video that what we did was we used the Taylor polynomial and we went out to the second degree, and then we truncated everything past the second order term. Well, to be able to get a second derivative, let's say we want to numerically estimate that. Let's say for some reason, we're going to go 2 steps beyond the initial point. Okay, so let's just say we have x sub I plus 2. And so what we're going to do is, just like we did in the first video, we're going to go through and we're going to expand the first, the 0th order, the first order term. So this is like our first derivative, and then our second order term. And then we're going to indeed go out to the third derivative of this. But this time what we're going to do is we're going to keep that second derivative. All right, and the reason we're going to do that is because, well, we want to approximate the second derivative numerically. So if we don't go out that far, we'll never get there. And so we're just going to truncate this. This is going to be our error. Like everything past here, we just don't care about that. And again, this is an estimate, okay? So now what we're going to do is we are going to go through and we're going to define 2h, all right, as going to be 2 steps beyond whatever the distance from x sub I plus 1 minus x sub I. All right, so remember, these are the steps. All right, so now we have 2 steps we're going to define as 2h. And we're just going to substitute that back in for each of these x sub I plus 2 minus x sub I. So we get this statement. All right, now we're going to pull some algebra magic. We defined f at x sub I plus 1 as this. Okay, so that was all the way back in the very first video we did that. Except we truncated this term. Well, now we're just going to kind of slip that in again. All right. What we're going to do is we're going to double this term. And why do we want to double it? Well, we're going to double it because eventually what we'd like to be able to do is to get rid of this term right here, this first derivative. All right. So if we can get rid of the first derivative term, all right. So we're going to have, this is our xi sub plus 2 and xi sub plus 1. If we double this and then subtract them, that means we would have 2 f prime x sub I h, and right here we have 2 f prime x sub I h, and we could just subtract f x sub I 1 and 2 f x sub I 2. All right, and that's exactly what we're going to do. And then we're going to get this yield. Okay, so we just basically take this stuff right here and this stuff, which is going to be from f x sub I 2. And then we just take everything from f x sub I 1. We just throw it into this really long equation right here. And we get this. And then we could just go ahead and combine like terms, because notice that we have -2 of the f prime of h, and we have +2 of the f prime h's. We have -2 f x sub I, and we have positive f x sub I. So that we're going to get a negative f x sub I. And now we have 4 divided by 2 of the f double prime h squareds. And here we have -2 times divided by 2. So we're going to have 1 of these. So we have 2 of these and 1 of these. And so that's just going to simplify into 1 f double prime h square. We add the f prime, or we add this f x sub I to the left-hand side. We divide by h square, and we get the forward difference formula for the second derivative. All right. Now, again, these are elementary sorts of equations, okay, or elementary sorts of formulas to estimate the first or the second derivative this time. In subsequent videos, we're going to take a look and see how we can get more efficient sorts of first or second derivative, third derivative, etc. But for right now, we're just taking a look at these higher order derivatives and basically getting our second derivative. Now, if you wanted the third derivative, guess what you would do? You would have f x sub I plus 3. And then you would take this, and this would be part of your Taylor expansion, but then you'd go out to the fourth derivative. And then you'd have to strategically try to eliminate the second derivative and the first derivative to get everything in terms of the third derivative. And then everything past that would be your error. All right, so this is sort of like the algorithm that you would use to numerically approximate second, third, fourth, fifth order derivatives. Just like we did for the forward difference in the first derivative, we could do the exact same thing for the backwards difference. And so what we could do is we could just subtract 2 from each of these indexes, and we could just go back to, and Notice that all we're doing is we're just subtracting 2 from each of these indices, and we end up with fx of I minus 2, fx of I minus 1, plus fx of I minus 2. And remember, these are the number of steps that we're going back, and h is your step. Just like we did before, what we could do is we could just get to our centered difference formula by adding those together and then dividing by 2. So in other words, we just take the forward difference, we take the backwards difference, we add them together, and then we divide by 2 to get the average of those. All right. And what you'll notice is that if you do that, we have an fx sub I, we have an fx sub I. All right, so that's 2 fx sub i's. We have negative 2 fx sub I plus 1, and then we just have our fx sub I plus 2. And eventually what we would end up with is we'd end up with this formula, all right, by substitution and just going through and simplifying it. All right, just like we did in before. All right, so pretty cool that we can derive these systematically at this point. All right, so what are we going to be doing at this point? Well, what we're going to be doing is we're going to be utilizing our second derivative, and I'm going to show you how to program it in MATLAB in the subsequent video.